cover section 6.7, the dot product, and this is the part 2 of the video. So we are on slide number 6, and we're going to talk about the projection of a vector onto another vector. And so this type of problems are very useful in physics. For example, when you have a problem like the image that we have here. So let's imagine that you have this boat, I guess, or what are they called? They're little lancha? Well, yeah, a lancha. What are they?
Jet ski? Lanch.
Oh, I can't think of that. Okay, so this mini boat. And so it is on an incline.
A motorboat?
And then it's starting to slow down, right? So what type of force do we need to apply to keep it there? And so we automatically know that there is something moving it, right? Perhaps the weight of the boat. And of course, combined with the angle of the incline that is formed with the ramp and the horizontal. And so to keep it from going in that direction, we of course need to apply a vector in the opposite direction, right? So it will go that way. And that's what I was explaining to you guys on the other problem. And so, well, right here we have that vector. Okay. Now, the vector that we see here, I'm going to trace it in red. That one is the gravity. And that one is perpendicular with the horizontal, right? We have a 90-degree angle. However, that vector is not perpendicular with the ramp. We have like this angle right here instead of 90. And so what we do is we're going to project the vector in red so that, some stuff here. So I'm going to trace the gravity one again. So now the one in green, that one will form a 90-degree angle with the rim. You could see it that way, or you could also see the tiny little box right here. Okay, so that's an example of a projection. Let's go over the next two. And so here we have vector W. It's kind of short. It has a smaller magnitude of vector V. And so what we need here is for this vector is the one that we're going to create, the one in red, all right? And so what we do is we draw this line. Well, you have to draw it. I'm going to teach you how to do it outside, okay? So you will draw this line. It doesn't matter if you go past that intersection. And then you're going to take the terminal point of this vector, and you're going to draw a perpendicular line with vector W after extending the length. All right? How do I know it's perpendicular? Well, because we're forming this 90-degree angle right here. And so now the new vector, this will be the new vector, okay? It's going to be from here to here. The one in red. Okay? And how do we read that? I want you to write this down, please. It's called, that vector, the name of it is the projection of, and then we take the big letter, which is V, projection of V onto W. The little subscript of the projection, that is what you're projecting onto. And so it's like we have this one, we shined a flashlight here. So this is the light. Just use your imagination, sorry. And so that's the flashlight, and then this one right here will be the shadow. Okay? So let me just pause this video for a second. Let's go now with the let's go over the other example. So now, don't talk. We have two vectors, but now vector W is in the opposite direction, right? Do you guys see it? Yes? Do we? Yeah? Okay. So then, here is the other one that we're going to project. The one that you see big here, that's the one that is going to get projected, all right? So what do we do? Well, we still need to take the terminal point from there and trace a perpendicular line. But perpendicular to what? We don't know, right? So what we have to do is extend vector W, and then once you have that 90-degree angle right there, that one will be the projection. Okay? This one. So imagine the flashlight is here. Oh, I'm using my drawing skills. Oh, yeah. And so this will be the shadow of it. Yes. Okay. Now, let's figure out how we're going to derive the formula that you will see here. All right? So let's go back. Okay, so we start with the statement given to us there. And that is because compared to this angle, theta, this is theta, right? And so we use cosine because we're referring to the adjacent side. So here's your right triangle, right? You guys see it? Right triangle? Yeah? Do we all agree? Right triangle. And so for this angle, the projection vector is the adjacent, right here. And then the hypotenuse is vector V. So it's right here. Now, since we're talking about the ratio, we're talking about numbers, not the vectors, the ratio of the numbers, so that's why we're taking the magnitudes, okay? Now, I'm using this just to derive the formula, so just watch and learn. I will not test you on it. Okay, so first step, we're going to take this magnitude here. What's the magnitude doing? To the magnitude of the projection. Dividing, so if I take it across, it's going to multiply, right? Like that. Okay, now from there, we're going to just use the reflexive property of equality and switch sides. But we're not changing any sign or anything, okay? So we're the projection of V onto W. All right, now from there, I want you guys to remember a formula that we derived last class. And it was the alternative, or alternate, I think, alternate dot product formula. And so we do have two, right? One of them is like you take the A components or the coefficient of the I components, you multiply them, and then you take the coefficients of the J components and you multiply them, right? The alternate formula for the dot product is it's something like you multiply the two magnitudes, and we found it by using the law of cosines. I don't know if you guys remember. But it was the magnitudes times the cosine of the angle in between them. Yes? Do you guys remember? I hope so. So now, isn't it true that this formula looks almost like this one, right? Except for one thing. The magnitude of W, right? But we know how to take care of things like that. So we could leave the dot product here, take the magnitude of W to the left side, So instead of multiplying, it will be dividing. And on the right side, we still have the magnitude of B times the cosine of theta. Now, what we're going to do is replace this expression that you guys see here with the equivalent expression that is here. Yes, are we okay if I do that step? So now the magnitude of the projection vector V onto W is going to be the dot product divided by the magnitude of W. Okay, and so now we have three equivalent expressions. This one, and this one. Okay, and so that is the formula to find the magnitude only. Now, how do we actually find the vector? And so what we do, this is the magnitude of the projection, okay? How do we find the vector? Well, do you guys remember something called the unit vector? Where we took a vector and then we divided by its magnitude. So I want you to, we're going to use that. Now, it depends which vector you're projecting onto what. And so since we're projecting vector B, we're going to use the following. Let's try it this way first. So we're going to use the following. The dot product that comes from BW divided by the magnitude of W. So that one is coming straight from here. Okay? And then we're going to multiply it by the unit vector. In this case, the one for W. And I will provide this formulas on the test, so please don't start getting worried about that. Okay. Now, if we were to multiply, oh, and then it's times, sorry. Oh, no, it's already done. So I want you to realize something here. This one right here is a vector in I and j terms. Okay? So then, if we multiply the denominators straight across, what are we going to get? The magnitude of W times the magnitude of W, so we get magnitude squared. Yes. Here we have the dot product of V and W, and then what we're going to have here is times W. But I want you to be very conscious of something. Out of here, you're going to get a scalar, a number. And this one is going to be in like terms of I and j. So then what you're going to do at the end, after you find the scalar, you're going to distribute that scalar to the coefficients of vector W. Okay? And I need to clarify, I would like to clarify that because sometimes you guys don't know, you have the formula, but you don't know how to use it. I've seen that on the test. So now let's go ahead and apply the formula. It's not as tough as it looks. And so it says here, find the vector projection of one vector onto another. So we have two vectors here, V and W. And we want to find this one. So what it means is that they want me to find the projection of V onto W. That's the subscript. And so the formula is going to be the dot product of VW divided by the magnitude square of W. And then we're going to multiply times vector W. So let's see. I'm going to do it by steps. So first, I'm going to find the dot product. So remember, that one will be given by multiplying the, and we have the two vectors here, so we need to multiply the coefficients of I, so 2 times negative 2, and then add the multiplication of the coefficients of j, so 4 and 6. And so that's going to be the dot product is going to equal to negative 4 plus 24, which is equal to 20. So that will be 20. And then what is the second? We need to find the magnitude of W. And then we square it. Right?
But since you're squaring the square root, wouldn't the square root just be canceled?
Exactly. So let's find magnitude of W squared. So we're going to have a square root, and then we're going to square it. So that's what Andrew was saying. So it's going to be, for magnitude, remember, you take each A and B, and then you square it. I have the formula on the board. Similar to Pythagorean theorem, so that will be a negative 2 square plus 6 square. And we already established the square root and the square are going to cancel. So 4 plus 36, 40. And my students were thinking about, oh, I already canceled the square root, sorry. We're thinking about simplifying it, but I told them, well, if you square a square root, the square root is going to be canceled, so there's no point. So it's just 40. Now here, I told you, you need to write vector W, but you need to write it in terms of I and j. So negative 2i plus 6j. 20 over 40 is just 1/2. So then we distribute the scalar, so scalar multiplication. So 1/2 times negative 2 is going to be negative 1. So we have negative I. And then 1/2 times 6 is like you're dividing, right? 6 divided by 2, so that is 3. So 3j. And that one right there will be the projection. Now let's look at the picture. So we started with vector V, is here. And then we had vector W, which is here. Right? And so we wanted to project the one in blue. Okay. So we trace this line. So remember, what did we do when this one was in the opposite direction? We extended that line, and then we traced the line so that it was perpendicular with it. And then that new vector, I'm going to draw it in red. That right there is the projection. Okay? So it's like if you have your flashlight here. Oh, I'm losing it. And then here was your shadow. Yes? Okay. Now, there is a problem for you to check. Unfortunately, we are almost out of time, so I will just leave it for you to do. The next one is the opposite of that. And so what we're going to do is decompose the vectors. Now, the formulas look a little intimidating, but they're not, okay? So let's see. We have two vectors that are non-zero. That's important to establish. And we can say that one of them, the first vector, vector v, can be expressed as the sum of two orthogonal vectors v1 and v2. So this is what we're saying. Vector v is equal to v sub 1 plus v sub 2. Right? So if we want to solve for v sub 2, what should we do? It will be equal to v minus, because this is adding, right? If I take this across, minus v sub 1. And so that's one of the formulas that we have here. And so what we need to do is find the decomposition of vector v. So this is what we're after. What is v sub 1? What is v sub 2? So then what we do is, and it's called decomposition, just so you know. So we're going to follow the formulas. And so first of all, we have to find one of them. So that will be the first step. Find, when you need to decompose, find v sub 1. And so you would use the formula that you guys see here. So we're going to need the projection vector, which is the same formula that we used on the previous example. I'm just following this, okay? So it's the dot product v times w, dot over w, divided by the magnitude of w squared, and then times vector w. So with that said, let's find, and it actually, this is the same problem, I think. I'm not sure. Okay, so, is it?
Yeah.
It is, right? Okay, so we already know this vector. You guys can look at it. It's 2i plus 4j, negative 2i plus 6j. Yes, it is the same, right? So I'm just going to take the vector that we found previously to save some time. Is that okay? Yes? So this one. We're going to take this one right here. Is it this one? Yes.
Yes.
Okay. And what was it? Negative I plus 3j. Okay, thank you. Okay, so now that we know one of the vectors, what do I do to find the second vector? It's right here. So we take the original vector v, which we know is here, and then we subtract the one that we found right here. And so that's going to be
I plus.
well, wait, 2i plus 4j, and then minus. Make sure you, I write them in parentheses because I like to do that so I don't forget to distribute the negative sign. So v sub 2 is 2i plus 4j, distribute the negative, so that will be plus I minus 3j. And so v sub 2, combine like terms, so it will be 3i
Minus j.
plus j, huh?
Oh, right.
So this is positive. So 3i plus j. And that's it for the problem. So you use the projection formula, and then you subtract it from one of the original. Okay, now the last one is very simple. And in here, we are considering work. Like this guy is doing some type of work, right? It's actually using, Taylor, can you please pay attention to me? So he is actually using, somewhere else. He's using his force to push a car, right? And so right here, we're actually going to consider that to be a vector. Work is a vector, and it's force. And what will be the magnitude of that? Well, it will be the force that this person is applying to the car. Okay, so I said that wrong. So work, the definition of work is going to be the length, like the distance, in this case from point A to point B, times the force that is being used, or the magnitude, which in this case will be 90. So 90 pounds. And then the distance is 200 feet. And so the work will be, what do you say, Andrew?
18,000.
18,000. And that's it. Now, what if we don't have those numbers? What should we do? Well, then we will find them. How will we find them? Well, we know how to find magnitude of force if it's not given to us. We have something in I and J. Let's say something like that. What would you do to find the magnitude?
Square root.
Square root of a squared plus b squared, right? Like quadrant. Then how can you find this? Well, there should be a certain angle that you will use for cosine. Why is this one just 200? What is the angle that we have here?
180.
No.
0.
It's just 0. It's just 0. What is the cosine of 0? 1. So that's why in this case we didn't have to multiply this one by the cosine of 0. So it was just 1. Okay? But if you have something on a ramp, like at an incline, then yes, you're going to have to multiply the magnitude of that, or the distance, times the cosine of that, which is the problem that we see here. And I'm going to finish it, and then I will let you. And so a child pulls a sled along level ground by exerting a force of 30 pounds on a rope that makes an angle of 35 degrees with the horizontal. How much work is done pulling the sled 200 feet? So we have the formula for work right here. And of course we have the alternative formula here. So far what we know is the magnitude of the force, because it's given to us, 30 pounds. Do we know the angle? Yes. It has angle of elevation of 35 degrees, which is the one formed by the rope in the horizontal. This is the horizontal, or here. So in this case, we're going to have to use the formula that we see here, and that's going to be the following. So magnitude of the force times the distance let's just say 200 feet. Well, I'm going to write the formula first. Times the cosine of the angle. So we substitute, this f will be substituted with a 30. This will be the 200 feet. And then here we'll have the cosine of 35 degrees. And that will be work. And so I'm going to give you the answer. That's going to be approximately, because it says it doesn't say how to round, so I'm just going to round it to the nearest whole number.
4,914.
The book has 15. What are the decimals after the 14?
Oh, 91.
Okay, so 15, yes. If it says to round to the nearest whole number. Okay, and that's it. I think the last problem is probably the easiest from the whole set. The next one is exactly the same, so I'm not going to do that.